Good morning, ladies and gentlemen. Dr. Steinitz, Charlie, Dr. Warren, colleagues, friends, and Jack. I am delighted to be in probably one of maybe the most important center today to help solve the terrestrial crisis we're in. Performance-driven design, analysis-driven design, data-driven design. I'd like to take a step back and talk about purpose-driven design. Why are we pursuing what we're pursuing? What is the goal that we are pursuing, and what is our common ground? So the word common is going to be slightly overused today, and I wanted to introduce or reintroduce the notion of the global commons. And perhaps telling you up front what I'm trying to tell you is that GIS and geodesign form a kind of a global commons, as we're very aware of, and I'd like to reinforce that notion by stepping into the world of the global commons to start with. But I'd also like to focus on something in this room, which is a global commons, which is invisible to us, and yet all-encompassing, and yet ignored, defaced, devalued. What is it? Something that we couldn't share more intimately in this room right now. The atmosphere. We're sharing the atmosphere, we're breathing each other's breath, we're sharing the molecules that make up the chemistry of the atmosphere. And through the atmosphere, we're connected. So all the other global commons that I'll be talking about, I want to, in this terrestrially bound focus of this conference, focus on larger global commons, which is probably key to solving the climate crisis to a large extent that commenced on the terrestrial global commons, and that's the oceans. When Magellan pointed to his later named Magellan Straits, not knowing whether they're going to go in the right direction, whether it's going to be really a shortcut or not. The oceans were a very different thing, not just physically, but also in terms of the mind of those inhabiting them. Now, Magellan inaugurated, and he didn't know it at the time, an age of what we call the mare clausum, the closed ocean. The ocean that's been occupied by seafaring nations and declared private. So particularly the Iberian countries, Portugal and Spain, closed the entire part of the global oceans for centuries. Until the Dutch East India Trading Company confiscated a Portuguese vessel, and a young lawyer from Delft was hired to defend the trading company. And he remembered, I think he remembered, you can't read it in any of the historical accounts, but I think he remembered Justinian law, the law of the Emperor Justinian, who developed the notion of the natural law, that commons, nature, oceans, seashores are not private, they're public. He developed the notion of the public, the civic, and the private in urban development. He said there should be three categories. It wasn't Creer, it was the good emperor of the 6th century. But of course, implicit in that notion was that it's also free to be taken, because that law said it's free, it's public until you take it, and then it's yours. So in building that, and also in the notion of the seas, was always the notion of an ambiguity. So international law now distinguishes 4 global commons: the atmosphere, the high seas, which we also call the areas beyond national jurisdiction, Antarctica, and space. And by space is not the universe meant, but the low Earth orbit, or the orbit that we inhabit. And so you see the attention is there already, because in other languages, global commons translated to public goods. They're there to be taken. They're for us. They're goods to be owned. So I'd like to come back to this notion of the global commons and say that perhaps things like the natural law that connects us all and that provides a kind of a basic framework of conduct, biosphere, not the climate itself, but a stable climate, is a kind of a common, a global commons, or common good. But also something I call the existential spheres, existential settings for our continued survival. Now this NASA blue marble of 2002 recaptured the 1972 blue marble, the picture, the famous picture from, you remember. This was stitched together using 4 months of data that were collected from board of the Terra satellite and this MODIS metering device. And manually, semi-manually, cartographers and information experts in 2002 spliced together this 3-dimensional image of the Earth. Later it was automated, done much more quickly, but it's now antiquated technology. But what did this unifying exercise and creating a one Earth out of many different perspectives that was accurate to a resolution of 1 square kilometer, later improved to 500 meters, did not really inaugurate a world yet of finding a global commons in dealing with the inherent challenges of the commons as they presented themselves. An alien who zips by Earth might ask, show me your orbit and I'll tell you who you are. And indeed, if you look at our orbit, that's what it looks like. Thousands of active satellites, some say billions, maybe trillions of small and intermediate bits of garbage floating around at various distances to the Earth. In a very short time, this is really 90% of the stuff was expelled, you could say, for purposes, individual purposes, within 10 years, 15 years at most, the most of it. So we're sort of asking ourselves, well, our relationship to that public common has been barred, if you will, that experience by our own conduct, individualistic conduct, who then has this fabulous twin star intermingled with SpaceX's satellites. So this is our emerging vision of the universe, and I think it's a time at which we have to ask ourselves, this technology which helps us understand ourselves so deeply, there must be a way of coordinating, integrating, and thinking about the future of this trajectory. Take another global commons, Antarctica, but I use the word cryosphere generally. Very well mapped, very well understood. This is a snapshot of that same MODIS blue marble model, cartographically explored, traversed many times, divvied up, divided up, and then fortunately in the last minute, almost before some sort of conflict breaks out over the resources of Antarctica after it melts down, a stop was made. Let's say no more dividing, we're freezing the subdivisions of those territories, and we'll scratch our heads and figure out what to do, because we know that's not the way to go. So I think it's another indication that we're on a right track, because all this effort, this understanding, intellectual effort, the cognitive effort, understanding the cryosphere, exploring it, traversing it, couldn't help or keep what is recorded here in this extraordinary analysis of the so-called Antarctic skin. This is the top 1 millimeter layer of the Antarctic cryosphere and its temperature change. Its temperature changes. And so this image shows you how the speed of the ice shelves accelerate towards the open sea, and recently Australian an international team of oceanographers discovered that this meltwater, it seems to be blocking the global abyssal overturning circulation. So the heat waves are developing at the bottom, the very bottom of the sea, because of this meltwater of Antarctica. Cool subsurface flow is being blocked. But at the same time, we in the Atlantic region know that the top layer is being blocked by also meltwater, now in the Arctic. So from both ends, we sort of managed to control the flow of this very vital oxygen and nutrient conveyor of the oceans. The connection to the hydrosphere, which is really encompassing all waters, including atmospheric waters, but really focused here most urgently on the oceans, is sort of my next chapter in this journey, and the focus on these extraordinary fish-like animals, krill, abundant, but even more abundant than krill are copepods. Now these little critters make up more biomass than all living animals combined. Gigatons of them. And they move every day 200 meters up and down. They move up during the day, jump on the phytoplankton, go down at night to poo, and in that pooing action deposit carbon. It's the most powerful carbon pump of the world. It pumps 30 times of the emissions of our industrialized nations in carbon cycling. So this is an extraordinary nano-robotic, but it's not robotic. These are like insects of the sea. They're less than a millimeter in length. And they munch on phytoplankton. They eat organisms that are even smaller than they are, but from a similar age. And here you see a 300-kilometer wide view of the Chukchi Sea of Alaska and the typical phytoplankton bloom that occurs seasonally there. And those phytoplankton blooms occur for various reasons, but they show that there is phytoplankton, because we should be concerned about that. 50% of that phytoplankton and other plankton has disappeared in the last 50 years. 50%. And so one message is, as a kind of a background to this very important focus of ESRI's work in the oceans and on land in understanding and helping solve the climate challenge, and particularly International Geodesign Collaborative's work that is commencing today. And I know that Professor Steinitz and his colleagues, including myself, will present it a little later following this. The biodiversity component is not just nice to have, it's an essential component to the climate issue. Because without biodiversity, there's no way to stop the climate runaway issue. And the reason for that is that biodiversity is essentially the carbon managers of the sea. And the sea are composed of 90% of the global habitat for animals and plants, 90% of it. And in the sea, we're very busy getting rid of it. There's 6 kilograms of bycatch in every kilogram of prawn caught. There's half of the seafood going to waste. 90% of fish stock is pushed to the brink. And the marine protected areas that we managed to actually put in place comprise only 6% of the oceans, many of them still open to fishing. And when you look at the areas beyond national jurisdiction, also the high seas, that's only 0.5% of that area is so-called no-take. The rest is open, slather. So the fundamental transformation has to take place, which is paralleling, rivaling all the other important transformations taking place as we speak. Marine shipping is so important to the global economy. 90% of global trade by volume, by value, are marine shipping based. $28.5 trillion in 21. And yet, animals are being struck all the time. 3% of the greenhouse gas emissions from that trade, and if you continue business as usual, that might rise to 70%. by 2050. But there's something else you see in that picture. You see a boat dumping the bilge water, the dirty water in the hold of the ship, illegally dumped on the open sea, and it's a common practice and being tracked by satellite. Individual NGOs like Sky Truth and others who are trying to understand where that occurs, but also beginning increasingly to identify these vessels and to prosecute them. So this oil slick is dramatic intervention in the marine ecology, as is, in fact, by the way, oil slicks coming off beach bathers. Do you see the lipid slick area that runs for hundreds of meters behind these two bathers that comes off their skin protection ointment, which contain chemicals which are vastly destructive to marine ecologies. In fact, so destructive that only one bottle will get rid of dozens of football field-sized areas of coral. It's an extraordinarily effective chemical that needs to be stopped. So when you look at the actual layers of the oceans and the understanding that the abyssal plain, that the lowest part of the ocean, is in surface larger than all terrestrial areas combined, this is what it's at stake. But few people realize that we talked about the skin of Antarctica, that this ocean also has a skin, which is called the sea surface microlayer. The generally is only a millimeter, the top millimeter of the ocean, across the entire 70% of the Earth's surface, has this microlayer, which is a living layer comprised of various microorganisms, phytoplankton, other organisms, in a kind of a lipid-like suspension, which have extraordinary functions, because it's not just the surface of the ocean, it's also the bottom of the atmosphere. It's where the atmosphere and the ocean interact very intensively. And here this shot shows you, in fact, the layers of the atmosphere very well. The lower 10 kilometers of this almost 600 kilometer deep atmosphere, only the lower 10 kilometers are the troposphere where we all breathe and live. Our airplane traffic takes place. Most of the animals live in the lower 10 kilometers. And 90% of the mass of the atmosphere is in this lower 10 kilometers. Above that, we have the stratosphere, mesosphere, thermosphere, exosphere. And the temperature in the exosphere is almost 2,000 degrees Celsius. It's an amazing stacking of temperature regimes, while in the troposphere we only have, say, between plus 20, 30, 40, and minus 50 degrees Celsius. So this heavy atmosphere sits on the oceans, connected to the skin, the sea surface microlayer, to the oceans. And through that transaction and the evapotranspiration that takes place and is controlled, in aerosols, clouds are formed, created by microorganisms in this layer. So this is the sort of function of the microlayer cloud formation, aerosol spawning, water vapor control, because we don't want too much vapor to escape, because, trick question, what's the most potent greenhouse gas? Water vapor. Water vapor, 75% of the greenhouse gas actions, except we don't mention it because we can't control it. We can only control it by CO2 control, and by reducing the temperature and reducing the evaporation from the oceans, can we control the water vapor, which is in fact a very important acknowledged greenhouse gas, but it's not subject to our action. We can't really do anything about it directly. That's probably good that way. But when the oceans lose that ability to control their evaporation, we'll have more steamy days, more vapor in the atmosphere, more feedbacks. Thermal transfer buffer, chemical exchange buffer, and that means CO2 exchange being slowed down by that. Now the bad news is that that skin has a skin disease. This is 1,000 black carbon particles that were filtered out of Atlantic Ocean water in 1 liter. Black carbon is the unburned part of wood fire, of coal fire, anything, the diesel that hasn't been burned properly falls out in black carbon and ruins this microlayer because it's being intervened with. And so the surface zooplankton is now cohabitating with that and with microplastic, which is the other big threat. Because microplastic looks like food, and this young chap, Calanus hegolanticus, recently has been observed by some scientists that began to reject algae because they looked to that animal like microplastic. Bad experience of choking on microplastic led this species to reject algae that looked like microplastic and reducing, of course, their intake. And so a bit of a question about Darwinianism here. The key question is that chemical interchange, CO2 plus water, gives you what? Carbonic acid. Now, carbonic acid, I didn't bring my Coke can, it's not very stable. It so it into bicarbonate ions and H2 ions. And the H2 ions, the hydrogen ions, are a measure of acidity. Now, the bicarbonate is nice to have, but we would rather have carbonate iron that the animals can use to make their shells. But the carbonate ions are being used to make bicarbonate ions and H2 ions. That's why we have this ocean acidification problem caused by fossil fuel burning mostly. And that's why we have a slight dilemma here. We have in red, created by the same team that did these measurements, a chart which shows you the decline in blue of marine life by 50% since 1950. And they're kind of projecting forward a trajectory. And in red, you see the progression of the pH levels, the decline of the pH level in the oceans. And pH levels are logarithmic. So what you have is at the current moment a pH level of 8.05. It was at 8.2 50 years ago. And if we continue the way we're progressing, we may be at a so-called point of no return just above 7.95, at which carbon-based, or let's say calcium-based or carbonate-based marine life will not be viable anymore. It just won't. And you say, well, we still have the other animals, but they, of course, use it as food, so the trophic collapse will take place if this isn't captured. Now, in yellow, you have the atmospheric response in bacteria, dinoflagellates, which produce toxic gases. So if we don't do anything about it, we're going right back to where we started millions of years ago with an atmosphere we couldn't breathe. Now, fortunately, when you look at that against the IPCC targets of SSP1 to 1.9 to SSP5 to 8.5 as the worst trajectory, we can now correlate that to the pH progression and see what do we have to do policy-wise to keep the pH level from dropping and therefore from all marine life disappear by 2045, according to this work. And so that's where we are now, 8.05. And this is where the point of no return might kick in. So that shows you that SSP1 to 1.9, SSP1 to 2.6 is the policy level we must keep as a minimum to avoid this kicking in of that acidification to a point where we can't be stopped. It becomes a chain reaction. And the four key messages are plastic pollution, is to stop, because it ends up all in the ocean. There's no other place for it to end up in. Coastal waste runoff needs to stop because of what it contains. Fossil fuel burning anyway, but many people in Europe particularly don't understand that wood fire is also bad. Wood biomass is also bad. Let me just move a little quicker. So we have, in fact, measures of trying to deal with the alkalinity or the acidity, maintaining alkalinity in the oceans called geoengineering. A lot of countries spending a lot of time and money on it. Calcium, acidity measures might make sense, but almost everything else doesn't make sense. The only thing that makes sense is shutting down fossil fuels, and this is something that we actually know what to do, how to do it, and just need to do it. So to conclude, the anthroposphere is the most critical area in which we know how to operate and that we can use as a lever to enact policy change. And the anthroposphere is finds itself in cities generally. We have this current vision that we live in cities, whether it's Hong Kong or Singapore or London, but for some reason cities have evolved into a unified vision of what a city is like, and it looks a bit like this. And it's almost a insult to Konstantin Doxiadis to call this an ecomonopolis, but Disney had tongue-in-cheek ideas about this. And we know that this kind of urban construct, a city that covers the entire planet, couldn't possibly sustain a photoshopped atmosphere, or an atmosphere at all. And it could only be based on one form of energy, and that's fossil fuels, because it engenders that kind of urban form. And so, while we have an increase in renewables in our mix, we also have an increased demand, so the 80% that I showed you remained constant. We still have 95% of transport energy being oil-based. These chaps are going out of fashion very, very fast, but until recently were still very fashionable, are still fashionable in some countries. And people don't usually think of the extraordinary water wastes that take place in making this energy possible. The costs in fossil fuel combustion is enormous. The health cost in the US is $600 billion annually. In China, it's $900 billion US dollars. And the military expenditures, the human cost of maintaining those sources to feed the war machines, to protect the sources, to feed the war machines, is beginning to dawn even on the defense departments. And this is sort of a trend that has to also now stop, and I think that's something that's very good. It's unnerving, but it's something we need to think about at the same time as we think about rejuvenating agriculture, because that's the other form of source of carbon dioxide and global heating, and also a source of the opposite that takes place on land from what takes place on the oceans, which is the drying. The oceans become wetter and the land becomes drier. Evaporation slowed down from the land, masses increased on the oceans. And part of the reason is this kind of agriculture which dries entire continents like Europe. So, happy birthday, Professor Drogi, 1952, I was born. This is how much CO2 emissions increased until then, but it had nothing to do with what happened since then. Bang. It's a sheer coincidence, and we share that. We share this legacy, which has to just, as quickly as possible, go back the other way. And it'll be a blip of aberration, which we just scraped the corner for. Now, we are now talking about Paris, 1.5 degree maximum rise. But I tell you, that's all marketing talk, because I personally know that by 0.6 degrees, the Arctic started to melt. 1.5 is hilariously wrong. We know it's wrong because we achieved this amazing feat of destabilizing the polar vortex and split it through stratospheric heat waves that occurred for the last 20 years. And that splitting of the polar vortex created this kind of weather which we know for several years, the bomb cyclones, the Texan freeze, and so forth. These are not winter aberrations, these are just Arctic desperation spilling over the rest of the globe, and as a reaction, the stratosphere, the winds, the jet streams also are thrown into a disarray, and prompting an increased aberrations, an increased emphasis on the so-called atmospheric rivers, or here in this case, the Pineapple Express hitting the Californian coast. Heat wave of 2019, the sort of first wake-up call that everyone remembers, the simultaneous heat wave, amazing, but caused by this choking of the stratospheric flows. the first awareness of forest fires, the emanation of carbon monoxide from those fires observed, not just in Brazil, but also the African forests to the right and the Siberian to the north. And I realized, well, gee, this might be a sort of a feedback mechanism, and indeed it is. Burning wood always releases things that we don't want, especially excess carbon dioxide, 280 parts per million in the atmosphere for the last 800,000 years. Now we've reached 220, actually topped 120 a little bit. So it's 150% above the long-term normal stable level. And methane, we've got long-term stable 600 parts per billion. And now we are 3 times there. 1900 shot up in parallel to the combustion madness. And so you might ask yourself, well, this temperature increase we just had from 13.7 degrees 1869 to 15 degrees 2023, where's the limit? Dr. Sagan and Stephen Hawking. And both had this sort of flippant response and said, well, if you don't watch it, keep in mind that it's only 15 degrees because the oceans take up so much temperature that if we didn't have the oceans, we now would have 65 degrees. It'd be pretty warm in here, but the air conditioner would have to run top speed. And if we don't watch it, we wind up at 250 degrees because maybe by 25, I only chose it because of the song some of you may remember. Because of the position of the Earth between Venus and Mars, Stephen Hawking says it's not a climate science problem, it's an astrophysical problem. You're positioned at a distance to the sun. If you don't have a protective biosphere, this is what you end up with. It's mathematics. And you could say, well, 25 is far away. But I actually did the math, and I looked at the fact that in the last 10 years, we had a planetary heat uptake of 100%. In other words, we doubled the heat uptake in 10 years by half a degree. When you measured the radiation at top of atmosphere, TOA. So how much goes up, how much comes in? The difference is the heat uptake in the atmosphere increased in 10 years, doubled. Now, if you double that, you need less than 9 decades to reach 250 degrees. Now, we just keep doubling. But why would we keep doubling? You would ask, why? But I'm asking, why wouldn't we keep doubling? So that's why this is such a logical response. Just stop doing it. Just don't do it. And reduce the emissions, forget about having a carbon budget that's long used up, and bring down the emissions as fast as possible, as quickly as possible, and realize that it's not a target we're aiming at, 1.5, we want to avoid it as much as possible. Ideally, we want to go back down to 280 parts per million, or focus on a level of carbon concentrations that are lower than the current ones, not higher. And an action horizon which is now, not in 2050. Because I don't know about any architects in this room, but architects and planners usually don't start their work until the year or just the night before the deadline. So 2049 is something we start, maybe we should postpone it, ask for postponement. So the carbon emissions is not 100%, it needs to be 150%. Reduce the emissions. And we can do that through ecosystem absorption, but also to one component that's ignored in this equation is biodiversity protection through anti-pollution measures. Because the biodiversity, particularly in the oceans as you saw, are very quickly able to recover. Those microscopic organisms double in population every 3 days. So if you stop dumping the lipophilic pollution, the microplastic, if you could stop that, that ecosystem would recover very quickly and increase its uptake of CO2 and also help with many other things. So the basis is a fundamental requirement. It's not a goal, but a basic requirement to keep the hemorrhage from flowing is the 100% renewable energy. And fortunately, we have that. We have fusion, nuclear fusion, in abundance. And it's conveniently located. We only need one reactor. And it makes us realize we have a And we don't have a lack of energy problem. We've got too much energy in the system. We just have to use it better. So that means transformation of the architecture, the urban settings, the framework in which we design our places, not around fossil fuels, but about solar energy. And not just our public infrastructures and our communal settings to turn into urban power plants, but also buildings like this building by a friend of mine. He designed this building to be a solar power plant. In other words, not as powerful as the coal-fired power plant to the north, but in a group able to supply the city with renewable power. There's a storage system, it's got a car fleet, it's got a way of tapping into waste heat from the sewage system. We know that we can do that on the open fields or fields that don't lend themselves to agricultural production, sell that on the market as pretty safe retirement investment. We know that we can, like in Burgenland in Austria, next to the Hungarian border, this is a state in Austria very poor that went from 0 renewables to 100% in 10 years. Just said, we'll do that. Great case study. And it was that, well, if you look at Liechtenstein, for instance, but also Liechtenstein being only 1% of the larger region of Lake Constance, could we do it there? And we ran a model, it's already 10 years old, by looking at the urban structure and the urban footprint, the syntax, the energy syntax of urban spaces, open and closed spaces that lend themselves to an analysis of prototypic energy responses. We spent a lot of time understanding how different parts of the city require and use and are able to generate different kinds of renewable energy sources. And so this is the range of sources that we looked at for that region, and we then categorized it into not energy parties that we are celebrating, but energy parties to project the demand, because we want to match the demand of energy with the supply of energy that suits that demand. And so there's a regional, very simplistic GIS model available, and we now applied it in Indonesia and in other countries to kind of understand the ability of this region to become energy self-sufficient, depending on different scenarios of efficiency in use and ramping up of renewables. And so time and time again, we also realized that this 2,000, 5,000-year-old technology of improving agricultural soil, or in this case, viticultural soil, in relative simplistic but policy-resistant ways, is a very important carbon reduction source. And if we do that and add it to our projection, we get a carbon negative region, a region that absorbs more CO2 than it emits. And so for this 15,000 square kilometer region, the per capita emissions measured directly on the ground, not the implied footprint, it can go from 5.5 tons per inhabitant to almost 1 ton. So it's about a 6-ton reduction just by the transformation of these measures. And then also a great cost savings, or let's say income generation to cumulative differential cost, jobs creation, and so forth. So they can apply that in a micro scale, this thinking, to the old pump jack regions. Figure out the economics, but I'm sure that can be solved. And then you have wonderful ways of thinking about what to do with that space. We can do it on a larger scale, like this 3 gigawatt coal-fired power plant consisting of 6 traditional 500 megawatt power plants near Berlin that we worked on for the last 6 years. It's a 8,000 hectare open cut coal mine, which 6 years ago we worked together with the local community in this town of Peitz and some other communities that are happily accommodating this power plant, and brought 12 students from all around the world, from different countries that have coal mine problems. Pakistan, India, Malawi, Australia, South Africa. And these international students worked with the local community for 6 weeks, and were sort of the draftsmen for these visions of what to do with this coal mine, because there was a conflict between the pro-coal and the anti-coal lobby. We said there's a third way going forward, and we want to see this transformed in some imaginary ways, but always in ways that are zero and ideally negative carbon, and while doing it also healing the water bodies, because the main water supply of Berlin flows through this coal mine, Spray River, and is polluted by it. So something has to happen in improving this waterway by transforming that coal mining and generating environment. Now, these are student ideas, like this Hungarian vision of a agrotourist, exploratory, bicycle-driven beer landscape, because he discovered it because of the sandy soil. There used to be all the ingredients for beer making in the Middle Ages. So bring that back, bring the bikes with helping wheels so people don't fall over, and there they go, explore the beerscape. But more seriously, this technological transformation requires storage systems, green hydrogen, transport systems, and so forth. Some students really focus on this industrial transformation. Some of them said, well, yeah, bioeconomy. What if we just let the forests take over, again in a studentish manner, but essentially also said, well, we need these kind of explorations or research into bioenergy, and then after all, this big open pit mine could house floating or just installed solar for some time. And there, at this end of the 6 weeks, there we are, and then we presented it to the coal-firing owners, a couple of Czech billionaires, who made out like devils because they paid €1 for this plant. And lo and behold, in 2021, they announced they're going to do exactly that. It's a coincidence, a bit like Charles de Gaulle said, the sign of great leadership is to seize the inevitable. And so, but I had to go there several times, present it to them. I think we're out of time, so I probably should close here, right? 5 minutes? Okay, well, that's 1 nanosecond per slide. The International Building is another project that I've been very centrally involved in. Is the transformation of this Europe's largest river island in the downtown area of Hamburg, which you see on top there, to a energy independent urban setting. Definition of projects, the spatial analysis, the projection of when renewable energy hits 100% supply, what do we do with thermal supply and CO2 emissions. And so there are about 70,000 people expected by 2050. And these are the 4 areas in which these were actually built, real projects. It's not just an exhibition for short-term expo, but this is real investment, 100 million euros of operational funds, leveraging 2.5 billion euros of investment by the private and public sector. In these 4 thematic areas, international competitions, floating houses, offices, self-sufficient houses with carbon retention, mad projects in algae production on facades. But the pride of joy of the local area is the biogas-fired co-generation plant, which is running a part of that central area, and the conversion of this old, this Nazi air defense bunker into a hot water tank for renewable energy storage, and also a dressed-up solar power plant that should have been destroyed, but the British forces didn't manage to pack it with TNT, and it didn't budge. It was completely destroyed inside. It should have been taken down, but 60 by 60 by 60 meter of concrete, 6 meters deep. Now houses a remembrance location up on top and a position to look over this. What is the future, kind of the sort of thinking of landscape as an energy system, as a climate system, climate and energy landscape. And so today you can get that app online, or you can walk there. And here's, for instance, the energy trail. There are other thematic trails that show places along there. And so I was just asking, in conclusion, myself and others, well, what if we did that globally? What if we try to understand what that all means in other kinds of technologies, whether it's allotment gardens in Zurich, whether it's seaweed farming in Bali, or whether it's differential plantation in Iran, boglands in Scotland, this reforestation projects that are ubiquitous in New Caledonia, for instance, or mangrove strengthening exercises. Mangrove being one of the three sort of ecosystems that actively take up carbon without cycling it again, the others being boglands and peatlands. Unlike forests, they really very strongly actively absorb carbon, but also the importance of maintaining old growth forests in themselves being the strongest carbon stock, and also the accretion of stock over time. Because anyway, we won't get into this now, but then we have these sort of urban features like water system swales. We don't really understand the carbon benefits, but we have now, thanks to the generosity of ESRI and the work that the IGC is doing, began to understand what that means, quantify the significance of these interventions, of these actions in carbon performance terms, and arrived at as a kind of a categorization of these across 8 different themes and topics. So, Copenhagen Postal Service, my favorite. All the posts delivered in Copenhagen is by bicycle. And then the pedestrian district of Nice. It's nice, but it's also something we can measure or understand. And it brings us back to this theme. Is there in our transformation of the understanding of our civilization, not just in terms of solar energy production and so forth, that's fundamental, but also in how we expel things into the ocean, individually, but also as a theme, as a topic. A transformation of the urban vision, also the urban imagination. And here at the end of this presentation, I had sort of envisioned maybe to call that geosphere, but that's a term that's already been used for different contexts, but there is some kind of term needed which points in the direction of GIS, but also geodesign. It's finding its home in that complex interaction of demands and responsibilities and rewards. Thank you very much.